Let's take a differential equation of the form. This is a nth order differential equation, and where f of x is non-homogeneous term when f of x is non-zero. And when f of x is 0, I have already covered this topic. Those are called the differential equations. Especially we focused on second order linear differential equations, homogeneous linear differential equations with constant coefficients in my previous lecture. You can refer them. So now in this video, we will be focusing only on non-homogeneous linear differential equations with constant coefficients. So this you can write it as, if you define, let d is equal to d by dx, the equivalent form of above one is like d square is equal to d square by dx square, and d cube is equal to d cube by dx cube. Third derivative and nth derivative is nth derivative by dx power n. Therefore, the given equation is, now this is becoming like a0 d nth derivative of y plus a1 d n minus 1th derivative of y with respect to x, a2 into d n minus 2 derivative of y with respect to x, and so on and so on. We'll be having a1 into d plus an minus 1, actually this must be an minus 1 into d plus an into y is equal to f of x. Equivalently, the same can be represented in the form of f of d into y is equal to capital F of d. I am better to write it f of x. So that is where capital F of d is nothing but a0 d power n nth derivative a1 d n minus 1 plus and so on plus a n minus 1 into d plus a n. So this is the form, and where you have taken this y's outside, where a naught, remember this, all these a naught, a n, a1, a2 and so on, a n up to n are constants. All these values are constant values. Let's say that this and then this all are constants. That's why we call it constant differential equation with constant coefficients. Now, so how do you solve this problem? So there are three ways to solve this problem. One is that operator form, then another one is method of undetermined coefficients, or variation of parameters. I'll be focusing on this video, I'll be focusing on operator form, that is you will be treating for homogeneous. First we are solving, whenever f of d into y is equal to f of x is there, firstly we are solving homogeneous ODE. So that is capital F of d is equal to 0, you are into y is equal to 0, you are assuming, and then solving for a polynomial either in D or in M. In M, when you assume y is equal to e power mx, be the solution. So where you are substituting y prime, y double prime, y triple prime and so on in the given differential equation of homogeneous form and finding the m value, that gives you complementary solution. Yc you are getting. So once you get Yc, we should get YPI, that is a particular integral solution. So how do you get the particular integral solution? So here I am using, to get the particular integral solution, that is the given differential equation is y is equal to this one, and then y I am writing f of d, f of x. So small f of x. So I have to solve this one to get the YPI. I have to solve this equation to get YPI. Once you get YPI, you will be writing y general solution is equal to general solution is equal to YC plus YPI. This is how we are actually solving the solutions. Form. Initially we start with a simple general method, actually we call it. So whenever there is an operator, let f of d is equal to d minus a, and f of x is equal to e power mx. So assume that there is a form of this kind. F of x is simply e power dx, that is your differential equation is something like e power mx. So how do you solve? We solve it using ypi. I am not focusing on y complementary solution because y complementary is easy to handle. So ypi is equal to 1 by d minus a, because as per the definition it is 1 by capital F of d into f of x. F of x is e power mx. Okay, you have a scenario like this. Now to write it further, and you look at this form and you try to adjust those terms. Let's say that d minus a, so e power ax into integration e power a minus ax into e power mx dx. So here d minus a you are writing as e power ax outside and e power minus ax in inside. That is, whenever exact form is represented in the inside, outside integral is with the negative sign of that one. So if that is the case, this is e power ax integration e power m minus a into x dx, and you know that integration of e power m form only. So the e power m minus a into x divided by m minus a. And now further if you simplify this, e power ax, e power mx, e power minus ax divided by m minus a, this eventually gives you m minus a. So this is your ypi. Then you are writing y general solution is equal to yc plus ypi. This completes your problem. If problem is neither initial nor boundary value problem, this is done. Otherwise, you have to fix those constants that are present in the arbitrary constants that are present in the yc part, complementary solution. So for example, find the particular integral of d square minus 5d plus 6 into y is equal to e power 3x, equivalent to, I mean this is nothing but so the given equation is equivalent to this one. So we have solved this type of differential equation by assuming y is equal to e power mx, especially the homogeneous part, and then y prime is equal to m into e power mx, y double prime is equal to m square into e power mx. We have substituted all those things. This is converting. We are getting a equation of the form. So anyway, e power mx cannot be 0. Therefore, you are getting the yc, y complementary solution. The other way to solve this one is that you can directly take d square minus 5d plus 6 is equal to 0 and solve for d. And this is like d square minus 3d minus 2d plus 6 is equal to 0. D is equal to 3 comma 2 are the roots. Therefore, yc is equal to c1 e power 3x plus c2 e power 2x. Of course, you are also getting here same situation. Of course, this implies that c1 e power mx, m is like 3 here, 3x plus another m is like e power 2x. So this is your solution. Yc, whether you are solving directly or you are using y is equal to e power mx form and then trying to fix m, both are same. Now the question is that how do you find ypi? So ypi is equal to, according to our definition, d square minus 5d plus 6 into e power mx. M is like e power 3x, e power 3x here. So that is the given equation. But you know that the denominator you can split it as d minus 3 into d minus 2 e power 3x. So according to the definition, you can write it d minus 3 into 1 by d minus 2 e power 3x, and this is nothing but 1 by d minus 3. We have seen that how to handle this. This is like e power 2x outside, inside with negative e power minus 2x, exactly whatever is there it is appearing. And of course, there is a function e power 3x, that's non-homogeneous term, and then this gives you d minus 3 into e power 2x, and if you try to simplify, it is e power x dx, because one is negative 2x, another one is positive 3x. Therefore, you will be getting e power 2x into e power x. This is 1 by d minus 3 into e power 3x. Now, again you apply the same technique, that is e power 3x outside, since negative, it is negative of negative is 3, and whatever is there exactly, it is minus 3x into e power 3x, this is from here dx, and if you simplify, this is e power 3x into x. You should get that solution as x into e power 3x ypi. This is y particular integral. Therefore, y is equal to yc plus ypi, that is equal to c1 e power 3x, c2 e power 2x, and then x e power 3x. So, this is the general solution. So, you can fix this C1 and C2 arbitrary constants C1 and C2, provided that the problem is either initial value problem or the boundary value problem. At the end, you can substitute those initial inputs or the boundary inputs, and then to fix the C1 and C2 here. C1 example, find the particular integral of the differential equation. Here I am not solving any homogeneous, I am just considering non-homogeneous, that is capital F of d into y is equal to f of x, that is e power, this is the capital small f of x, non-homogeneous term, this is the non-homogeneous term. So, here f of d is something like d square plus 4d plus 4. So, you can write it as equivalently d plus 2 whole square. You see here earlier the fraction was in the denominator, it was d plus 3 into d plus 2, now repeated, now it is d plus 2 is appearing twice. So, same term it is appearing twice. So, how do you solve this problem is a question. Now, to find ypi, we are writing into f of x, that is equal to 1 by d plus 2 whole square and minus x square e power minus 2x, and this is nothing but minus of 1 by d plus 2 into 1 by d plus 2. You can write it always. So, x square e power minus 2x, this negative is adjusted here in the beginning. Therefore, this is 1 by d plus 2 into, you follow the same procedure. Since this is whatever the term is there, this opposite term is coming, opposite sign term is coming outside, that is plus 2 is there, e power minus 2x is coming in, x square e power minus 2x, this is a given term, and that must be multiplied with e power 2x dx. Whatever is given, it must be coming exactly in the form of this one. Therefore, if you try to simplify this, minus 1 by d plus 2 e power minus 2x, if you try to simplify, this is minus, actually minus. So, this is integral. So, x power minus 2 dx is left over, because this and these two terms are becoming 1. Therefore, therefore, you have to simplify further, that is e power minus 2x into, what is this term, x square integration is minus x power minus 1. Otherwise, you have to write it minus 2 plus 1 divided by minus 2 plus 1. This is giving actually minus there. This is 1 by d plus 2. Since there is a minus and minus into minus is becoming plus. So, e power minus 2x into x power minus 1, x power minus 1, which is already there. Now, again use the same concept, e power minus 2x, and inside it must be of the same sign, e power minus 2x, x power minus 1 into e power 2x. The same term should appear inside. Outside is minus 2x. You see that e power minus 2x is appearing outside. This is x power minus 1 dx, and further if you simplify, this is actually 1 by x is ln of x. This is the solution to the particular integral solution, we call it ypi. There are shortcut methods to solve this. I mean, no need to write this many steps, but there are obstacles there where this denominator may be 0 whenever you replace d by minus 2, that we will see after some time. So, there are techniques to avoid this many steps actually. So, there are many steps which are involved, and suppose whenever you have a scenario like your f of d, for example, f of d into y is equal to f of x, but this f of x is involving several functions with something like this, then you can apply ypi1 with 1 by f of d into x, and ypi2 is 1 by f of d into e power x, and ypi3 which is sin x divided by f of d. So, you can sum all these solutions at the end. Ypi is equal to ypi1 plus ypi2 plus ypi3. It follows the principle of superposition, which is also a solution altogether. You can do it separately for each term and then you can club it after some time. So, it is up to you how you are going to solve it. Find the particular integral of y double prime minus 5y prime plus 6y is equal to ln of x. You see here, so we are only finding ypi, which is equal to 1 by d square minus 5d, because there is a derivative. Therefore, derivative is represented by d. So, double derivative is represented by d square into your f of x is small f of x is ln of x. So, this is that, and then you know that how to split it. This is d minus 3 into d minus 2 ln of x. Now, you are applying the partial fractions instead of applying the product rule, because you know e power x ln of x is integration is whenever you have e power x and ln of x, this is going to be very complicated function further and further. Instead of handling this problem in the similar way, what I am going to write is that d minus 3 1 by d minus 2, the adjustment is minus 1, it can take care of the form. Therefore, 1 by d minus 3 into ln of x minus 1 by d minus 2 into ln of x. You have 2 ln of x, and this is nothing but, if you write it, e power 3x outside, inside it is e power minus 3x ln of x dx, and minus e power 2x integration ln of x e power minus 2x dx. So, this is not easy to handle, because whenever you have a this exponential integrations is actually eventually leads to a simple form of whenever integration of e power x ln of x dx is there, you can write it as e power ln of x, and there is a series which is actually even if you use bipartitions, you will be getting integration e power x divided by x dx as a second part, and which is nowhere it is going to be end. Therefore, you are getting a series that actually we call it a special function, and that is actually holding all these terms. So, this is how we are actually solving the solution. For example, we are trying to solve this problem, but main intention to find the ypi is equal to d minus 1 whole square d plus 1 whole square e power x, and we actually don't want to apply this the earlier discussed method like in the previous example where we have used the partial fractions to solve this one instead of solving this problem. This way we are trying to use instead of this repetition we use the partial fractions. So, what is that partial fractions advantage? Here you have to use repeatedly one upon the other integrations. We have to apply the first two problems are discussed on this in the same way. Here actually you are using partial fractions. So, when you use partial fractions, you will be having the fractions like this, plus 1 by d plus 1 whole square e power x. So, with this here there is a disadvantage. This disadvantage is at this location you are applying e power x, that is outside, right? Yeah, e power x, yeah. So, disadvantage is that here you have to apply 2 times the integration, here also 2 times, that is 1 by 4 times. You look at that minus 1 into, so according to this the minus sign is there, therefore it must be with plus sign outside. Integration of e power x into e power minus x is inside dx, and plus 1 by d minus 1 whole square is there. That means you have to apply 2 times the same thing, integration over integration. That is actually first you can apply, and it is giving e power x integration e power minus x e power x dx, and the other one is that e power minus x outside and e power x inside e power x dx, and plus 1 by d plus 1 into one integration only I am applying. So, e power x into e power x dx. So, this you have to again simplify one more time here, this one and then this one you have to simplify one more time, and that is 1 by 4 times it is minus e power x, and these two are adjusting, therefore it is 1 only, integration of 1 is dx, plus 1 by d minus 1 into e power x into, again these two are adjusting, that is again 1, this x into that one, and plus e power minus x into e power 2x is coming, therefore e power 2x by 2, and the other term is similarly 1 by d plus 1 into e power minus x, e power 2x by 2, and again you have to simplify these two terms one more time by applying that. So once you apply that, ypi is of the form minus x e power x, nothing to do with that term. The other term is giving x square by 2 e power x, the e power x by 2, which is nothing to do. This is also free from the integration. 1 by d plus 1, you have to treat it again, simplify it. That simplification leads to e power x by 4, e power x by 4. So this is your solution of ypi actually. You are finding the particular solution, but before you find, this is a solved equation, therefore yc you have to focus, that is d square plus 1 is equal to 0, or m square plus 1 is equal to 0. This is giving complex roots, therefore solution is yc is equal to c1 cos x plus c2 sin x. There is no real part in it, it is plus or minus I only, therefore c1 cos x plus c2 sin x is your complementary solution, and ypi is equal to 1 by d square plus 1 secant square x. Now you see here, how do you simplify it? If you write it using the earlier one, it won't work. So therefore you have to split this d plus I into d minus I into secant square x. And now further you are actually trying to simplify further, using 1 by d plus I and 1 by d minus I. So to remove the d, it is minus sign, but maybe, yeah, but this is giving 2i, so the other way, so the 2i is adjusted here, therefore it is exactly same as the previous one. Now if you take inside, actually this is 1 by 2i 1 by d minus I secant square x minus 1 by d plus I secant square x. You can write it secant square x as 1 by 2i into 1 by cos square, you can write it, but d minus I, how do you write it? D minus I is e power ix integration e power minus ix into secant square is 1 by cos square x dx, and the other part is that minus 1 by, so since plus is there, plus should go inside, negative should come out, and then integration of e power ix 1 by cos square x dx, and this is the part we have to simplify. This is 1 by 2i, you know that e power ix, and integration e power minus ix is nothing but cos x plus I sin, cos x minus I sin x divided by cos square x dx, and the other part is that minus e power minus ix and integration of cos x plus I sin x divided by cos square x dx. And here what are the terms you will be seeing? There will be a cos x by cos square x, that leads to secant x, and then another term is cos x by sin x by cos x, that is tan x, and then divide and 1 by cos x is there, that is secant x. So if you simplify, you will be getting e power ix into integration of secant x minus I secant x into tan x dx, and the other part is that minus e power minus ix into integration of secant x plus I secant x tan x dx. So now there are two terms. Now if you further simplify that, that leads to a new form of this is equal to 2i into e power ix into integration of, if you try to simplify the, collect those terms of e power ix and e power minus ix, which is only holding the term secant x dx. So here and here, which is only holding the secant and secant terms. The other terms are, if you take the other terms, minus I into e power ix plus e power minus ix is multiplied with tan x secant x dx. And now if you simplify, this leads to a simple form 2i. Oh, I'm sorry whether it is 1 by 2i. Sorry, 1 by 2i. 1 by 2i. 1 by 2i, and therefore this is actually giving this term is, if you try to take inside, this is giving 2i sin x ln of secant x plus tan x, and minus 2i times cos x secant x, and after simplification this leads to like sin x ln of secant x plus tan x minus 1. So that's it. This is the particular solution. Therefore, if you want to write a general solution, y is equal to yc plus yp, that is c1 cos x and c2 sin x plus secant x times ln of secant x plus tan x minus 1. That is the general solution. So you can solve it this way any problem, but this is little lengthy. Now we are moving to shortcut techniques. Shortcut techniques we are trying to use here to reduce the time. So whenever capital F of d into y is equal to f of x is given, then y is equal to 1 by f of d. We are using the same technique, and instead of using 1 by d plus a some f of x is equal to e power minus a x e power a x f of x, and doing it repeatedly or partial fractions, we are trying to avoid this technique, this method. So if you have some control over it, what are those controls? Cases, you see that case 1, suppose your f of x is simply e power bx, some exponential form, then your ypi is equal to 1 by capital F of d into f of x, but that is 1 by capital F of d into e power bx, and the output is always e power bx into 1 by f of b, provided that f of capital F of b is non-zero. So whenever capital F of b is non-zero, for example, solve the differential equation. For example, solve the differential equation y double prime minus 5y prime plus 6y is equal to e power x. We know that yc is equal to c1 e power 3x and c2 is equal to e power 2x, and ypi is equal to 1 by d square minus 5d plus 6 into e power x. Here f of x is equal to e power x, but if you compare general form e power bx, b is like 1 here. Therefore, coefficient of x is 1. Therefore, I am just calculating what is this value at x equal to at d is equal to 1. At d is equal to 1, because coefficient is 1 here. X coefficient is 1 in the non-homogeneous term. So when this is 1, which is equal to 7 minus 5 is 2, which is non-zero. This is non-zero. This is equal to, therefore, 1 by 2 of e power x. This is the ypi. You can check the same thing by comparing the previous one. If you split that into two parts, e power x, either you can take partial fractions. Here I am applying directly d minus 3 into, if I apply for with this e power 2x integration e power x into e power minus 2x dx, and this leads to 1 by d minus 3 e power 2x integration of e power minus x dx, because this is minus 2x, the other one is e power x. This is giving 1 by d minus 3 into e power 2x e power minus x by minus 1, and further simplification leads to minus 1 by d minus 3 e power x is the output. Again, since d minus 3, 1 by d minus 3 is there, we have to apply into e power 3x integration of e power x into e power minus 3x dx. This gives you like minus 1 into e power 3x into integration of minus 2x dx, which is equal to minus 1 into e power 3x into e power minus 2x divided by minus 2, which is equal to 1 by 2 times e power x ypi. So this one is exactly same as the other form shortcut, both are same. The shortcut method is always acceptable provided that it is of this form, e power bx form only, and whenever you replace the coefficient of x by derivative, and it should not be 0. That's why we have used f of e power bx, and where capital this is non-zero, that operator is replaced by coefficient of x here, and that must not be 0. Whenever that is not 0, directly you substitute that, replace the derivative terms by coefficient of x. Here the coefficient of x is, whenever exponential form is there, coefficient of x is 1, and you are replacing, you have identified this is non-zero, therefore you have concluded solution is this. This is very quick, very easy to handle, and this is the first case. There are several cases. So case 2 is when f of b is 0, that is capital F of d into y is equal to e power bx is your solution, but here in this case capital F of b is 0. So we have identified that the moment when you substitute, this is becoming 0. So then how do you handle such scenario? So this is very easy to handle, and assume that given ODE is of the form d minus b whole power r times it is appearing. Suppose d minus 3 into d minus 2 is there, then r is like 1 1 in each case. So so you have a situation when f of b is equal to 0, that is the given differential equation. If you replace derivative by exponential bx, that is coefficient of x is b, then f of b is 0, then we have to understand how to get the solution. Suppose the given differential equation is d minus b whole power r, I mean some coefficient is or some root is actually appearing r times, where r is a positive integer, then the particular integral solution is given by ypi is equal to 1 by g of b, where g of b is non-zero, a new function which is a splitting form of the given differential equation, and e power bx, and 1 by r factorial into x power r. So this is you are adjusting here. So how to, that adjustment is given where if there is no repetition, let's say that 1 by d minus 3 into d minus 2, only it was appearing only one time. Whenever e power 2x is there, d minus 2 is 0. Whenever e power 3x is there, d minus 3 is becoming 0, but r is repeating only one times. So that time it is 1 factor into x power 1, that is x1, directly you can write it, where g of b is like for example you have a scenario f of d into y is equal to e power 3x plus e power 2x, and where f of d is like d minus 3 into d minus 2. So if you are handling this situation, if you look at that ypi is equal to 1 by d minus 3 into d minus 2 into e power 3x plus 1 by d minus 3 into d minus 2 into e power 2x. Then you look at this here, because of 3 this is becoming 0, and because of 2 this is becoming 0. Therefore I can write it as, here powers are 1 only, so r is like 1 only. So if you want to solve this, I can substitute here 1 by 3 minus 2. So that is g of b is, g of d is actually 1 by d minus 2. Therefore g of 2 is actually g of 3 is actually 3 minus 2. Directly I can substitute. But issue is with the other term, that is e power 3x, and 1 by, what is r here? R is appearing only one time, and then x power r, that is x power 1, plus similarly here this is the issue is with the g minus 2, therefore 2 minus 3 is, you can substitute directly, and e power 2x, because you are handling 2 only, and how many times it is appearing? Only one time, therefore 1 by factorial into x power 1 you are getting. So this implies e power 3x into x, the other one is minus x into e power 2x is the solution, y particular integral for the differential equation y double prime minus 5y prime plus 6y is equal to e power 2x plus e power 3x problem. Especially particular integral is this particular integral solution. So this is how actually we are solving whenever there are cases. So for example, we are solving one more problem which is of this kind. This is like d cube minus 8 into y is equal to 60 e power 2x. Therefore, we are only finding the particular integral, but if you want to solve the yc, this 2 is one root, therefore c1 e power 2x you can get it immediately, and you have a complex root, the other, because 3 roots are there, another complex root is giving minus 1 plus or minus I root 3, therefore that is giving a constant times cos root 3x plus another constant times sine root 3x. So this is the yc, and we are moving to yp. Ypi is equal to 1 by d minus 2 into the other roots are something like d square plus 2d plus 4 is multiplied with 60 e power 2x. You see, the problem is with 2 only this case. The other value d square plus 2d plus 4 at d is equal to 2 is 4 plus 4 which is 12, which is non-zero. Therefore, this part is well defined. Only issue is with 1 by d minus 2. So, according to the earlier previous definition, 1 by d minus 2, this is 1 by 12, 60 e power 2x. The issue is only with this term. We have seen that the equation is 1 by 12. This is like g of 2. This is like g of 2, and you have 60 e power 2x, of course e power 2x, and then this term is there 1 by d minus 2. It is appearing only once, therefore 1 by 1 factorial into x power 1 we have to write it, which is eventually e power 2x into x. So 5x e power 2x is the particular integral solution. Therefore, y general solution is c1 e power 2x plus e power minus x into a cos root 3x plus b sine root 3x. This is from the homogeneous. The non-homogeneous term is this one. So, the y particular integral solution is this one. This completes the problem. So, this is case 2, and then case 3, what if you have, if small f of x is like sin bx or cos bx. So, what if capital small f of x is this one, that is non-homogeneous solution is this one. Recall e power I ax is equal to cos ax plus I sin ax. So, we have to remember this formula, we have to recall this formula, then you can understand that if this is the case, whenever d is there you are replacing replace d by ia because I is there, e power ia is the coefficient of x, then d square you are going to replace with ia whole square, which is equal to minus a square, as I square is equal to minus 1. So, we are doing the same technique. Again, issue is same, the denominator should not be 0, that is capital F of d should not be 0. If that is 0, there are issues. So, you can think about the situations like the cases where it is not 0, but you have to look at that if f of x is equal to sin bx with this process, with the above process, only sin bx is present. F of x is equal to sin bx form. This sin bx, if you recall this e power iax is equal to, it is I times sin bx. In this case, you have to take only the complex part of the solution. Suppose you are handling only with cos bx, then you have to take a real part in the particular solution. Why I am specifying? So cos bx is corresponding to the linear real part, and sin bx is corresponding to the, so because cos bx corresponds to real part, sin bx corresponds to the complex part. For example, you are solving the differential equation y double prime plus 4y is equal to 15 cos 3x. So you know that yc is equal to c1 cos 2x plus c2 sin 2x, as d square plus 4 is equal to 0. It is giving plus or minus 2i are the roots. There is no real part, therefore simply complex part is contributed. I mean c1 cos 2x plus c2 sin 2x is the complementary solution. And then moving back to ypi, which is equal to 1 by d square plus 4 15 cos 3x, which is equal to, you try to replace d by 3. So if you replace d by 3i, which is giving minus 3i plus 3i whole square plus 4. So if you replace d by 3i, it is 3i whole square plus 4, which is equal to minus 1 by 5, as d square 3i whole square is minus 9, minus 9 plus 4 is minus 5, 15 cos 3x, which is equal to minus 3 cos 3x. Here I got this solution directly. So you may refer here earlier we have used real part and complex part. There is no complex and real here, directly we are able to get it, how that is matching. So if you ask, if that is the case, d square plus 4 15 cos 3x, you can write it as, I mean if you try to write cos 3x is there e power I 3x, which is involving both cos and sine. Then you can write it 15 times e power 3ix, and you can write it denominator as d plus 2i into d minus 2i, you can write it, and this is like I 3x. If you try to expand this one like the previous cases, you will be getting that real part plus imaginary part. So the solution is actually real part. So that's what I was trying to. If you follow this method, the basic method, you will be getting the same structure. Here, since it is non-zero, directly I can substitute d square by 3i square, the coefficient of this one, and then I am able to get the solution directly. The solution is a combination. So if you look at that another problem, solve the differential equation y double prime plus 4y is equal to 8 cos 2x. There is an issue. D square plus 4 is equal to 0 implies yc is equal to c1 cos 2x plus c2 sin 2x. That is clear. I mean no issues. But the problem is that when you try to calculate ypi, you have a scenario like this. E power 8 cos 2x. The moment when you substitute d square is equal to 2i whole square, minus 4 plus 4 is 0, as d square plus 4 is becoming 0. So hence this is, you cannot move further. This substitution replace d square by coefficient of x, that is 2i, is not acceptable. So to deal with this, what I am going to do is that I am going to convert this into the previously discussed method, general method, that is I am writing cos 2x as e power I 2x. Now you see here, I am not adjusting anything, I have taken the general form. How the cos and sin are related, it is like e power ix only. So therefore I have taken that, and I am further writing this e power d minus 2i into 1 by d plus 2i into e power I 2x. Now you look at this, this is non-zero. So therefore I can replace 8 by d minus 2i. If you remember, that is like x times, we have seen that repeated case in the denominator, where we have used 1 by g of b into e power something into 1 by r factorial into x power r. But here it is appearing only one time. Therefore we can take care of that one. So if you replace d by 2i, now it is 4i e power 2ix. Now the issue is with only one term, but this power is also 1 only. So therefore I am replacing this term with the another form, that is like 8 by 4i into e power 2ix. Now I am applying, this is 1, therefore I am writing 1 factorial into x power 1. So this is giving something like, if you try to simplify, this is 2 times, there is a I here, if you write minus I whole square is minus I, sorry, so plus 1 is there, plus 1 I can write it as minus I square and 2 e power 2ix into x divided by I. Now I can cancel, I can simplify that as minus 2ix into e power 2ix. In the expansion you will be seeing that minus 2i into x into cos 2x plus I sin 2x. Now cos contribution is only real part, therefore you have to see that this is 2i into cos is imaginary and imaginary into imaginary is real. Imaginary into imaginary is real, this is real. Therefore you will be getting only when you take multiplication minus 2 into I square into x into sin 2x. This implies 2x sin 2x is your ypi. Y particular. Therefore, yc is equal, y is equal to c1 cos 2x plus c2 sin 2x and then plus 2x ypi is sin 2x. This is what I was referring earlier. So you have to be very careful when the denominator is becoming 0 or when the denominator is not 0. So case 4 is when f of x is of the form a polynomial. Polynomial. Whenever this is a polynomial, how do you handle this? So therefore the procedure is as usual. The procedure is as usual. We have to do a little calculation, that is f of d into y is equal to f of x. The ypi is equal to 1 by f of d into f of x. Now you have to take a call based on the f of d. So for example, so you are solving a problem, solving a differential equation of the form y double prime plus 4y is equal to 8x cube. So here the polynomial is appearing, earlier it was exponential and then sine, we have solved sine type of problems also we have discussed. Now this is a new form. So for this yc is actually same thing, c1 cos 2x plus c2 sin 2x, there is no change because you are getting complex roots plus or minus 2i. For ypi, which is equal to 1 by d square plus 4 into 8x cube. So how do you solve this type of equation? Since only polynomial is there, 1 by d square or d stands for the inverse of the derivative. So I want to handle this problem in the derivative form by taking 4 common and then writing d square by 4 into 8x cube. This is nothing but 2 into 1 by 1 plus d square plus 4 into x cube. The idea is that if I take this to the numerator, this is 1 plus d square by 4 whole power minus 1 x cube. This is 1 plus x whole cube, 1 plus x whole cube. That is, if you expand that, this is 1 minus d square by 4 and the other term is d square by 4 whole square plus minus and so on and x cube. So I can see that this is a polynomial of degree 3 more than third derivative, it vanishes, it is 0, it vanishes. Therefore this is equal to 2 into x cube minus 1 by 4 into d square x cube plus 1 by 16 into d power 4 x cube and so on. You see that these are derivatives. The moment when you apply derivatives, minus 1 by 4, first derivative is giving 3x square, the other derivative is giving 2x. Therefore if you apply 2 times derivative, this is 3x square into 2x. Therefore, this is becoming 1 by 16 into 4 times derivative. Third time derivative, this is a constant. Fourth time derivative, this is 0. All future terms will be 0. Therefore, you have to stop at third derivative of maximum, that is equal to 3 by 2 times x, and all other terms are 0. So, you are handling this problem in other way, that is 2x cube minus 3x. You are handling this problem in other way to find the YPI. Here you are not replacing derivative by something. Here you are trying to solve this problem by converting 1 by derivatives in the form of the simple formulas like 1 by 1 plus x or 1 by 1 minus x or the whole squares. You are simply applying derivatives directly to simplify it. That is the advantage of this one. So another case is that, so we haven't taken any mixed cases. Your f of x may be of the form e power bx into g of x. So how do you handle that situation? So for example, we'll see that. So in this case, ypi is equal to 1 by f of d into e power bx into g of x. And if f of b is non-zero, then if f of b is non-zero, then e power bx you can pull it out by replacing derivative by d plus b g of x. So a problem of this kind. You look at this, d square plus 2d plus 5 is equal to 0. The homogeneous part is giving minus 1 plus or minus 2i. Therefore, yc is equal to e power minus x is common, that is the real part contribution, and then a cos 2x plus b sin 2x, or if you want to write it, you can write it c1 cos 2x and c2 sin 2x, that is because of the complex part. And now to find ypi, you are writing 1 by d square plus 2d plus 5 e power x and then x into. So now you see e power x. Usually it is must be e power bx. B is like 1. So what have you done? We have to do, earlier we have done replace d by d plus b. B is 1, therefore d plus 1 whole square plus 2 into d plus 1 plus 5 into x. So e power x, and if you simplify, this is d square plus 2d and then 2d 4d, and this is 2 and then 1 3 plus 8 into x. You will be getting something like this. So here I am pulling 8 outside, therefore I am getting a structure like 1 plus d square plus 4d divided by 8 whole power minus 1 of the form into x. If I pull it here, I can pull 8, I can write it as 8 times 1 plus d square plus 4d divided by 8, and then I am bringing that term to the numerator, that is e power x by 8 into, now you expand it, 1 minus d square plus 4d by 8 and so on into x. No need to worry about it. This term itself is having derivative. Since x power 1 is there, first derivative itself is constant, all future derivatives will be 0. Therefore, no need to consider all these future terms. Simply it is x minus 4, d square derivative is 0. So that is 1 by 8 times d square x is becoming 0, and the other term is minus 4 by 8 into derivative of x. This is only survival term, and apart from the first term, 8 minus 1 by 2 into 1 by 2 into 1. This is the output. If you simplify further, this is 1 by 8 x e power x minus 1 by 16 e power x is your ypi. So this is how we are solving all kind of problems. The last problem is that you may have like this is the case 6 or case 4 is discussed. Case 4. This is case 5, and then last case is case 6. Case 6. Case 6 is your f of x is of the form x power m into v of g of x where g of x is of the form cos ax or sin ax. We have a differential equation of this form. You know that yc is equal to c1 cos x plus c2 sin x, as plus or minus I is the solution to the roots to the homogeneous differential equation. And to find the ypi, you have to write it 1 by d square plus 1, and x square sin 2x you have to take it. You know that whether okay. So, this case you have to convert that into e sin 2x as e power 2ix, and we have to consider the complex that is imaginary part. We have to take imaginary part. So, if this is the case, you are replacing derivative by e power 2ix d by d plus 2i x square. So, this is e power 2ix, and if you simplify, this is d square plus 4di and minus 4 plus 1 into x square. So, this is e power 2ix 1 by d square plus 4di minus 3 e power x square, and if you take minus 3 outside, minus 1 by 3 e power 2ix 1 by 1 minus d square plus 4di by 3 into x square. Now, you have to again expand it using the 1 by 1 minus x whole square minus 1 by 3 e power 2ix, and the first term is 1 and the second term is d square plus 4di divided by 3, and the other terms are something like d square plus 4di by 3 whole square and so on into x square. All future terms are 0 because this term itself is d power 4 and then d cube and d square. So, since the given polynomial is second degree, therefore, better to stop there itself. Therefore, minus 1 by 3 e power 2ix, it is x square. First derivative of that is second derivative of that is 2, and then 4di is giving 4 into 2xi, and this term, among all these terms, only survival term is 4d by 3 whole square only, that is minus 16 d square is 2 divided by 9 actually, that is the only survival term. All are 0, all will be 0, and therefore minus 1 by 3 e power 2ix into, if you take the constant terms, this is x square and the other term is plus 8 by 3 xi. The constant term is here, it is 3 by, so therefore 6, therefore minus 26 by 9 if you simplify, and there now you need to write it 1 by 3, you expand it cos 2x plus I sin 2x, and the other term is like x square plus 8xi by 3 minus 26 by 9, minus 26 by 9. If you try to find all possible cases of the particular solution, now you try to look at that only the complex, because sin x corresponds to complex roots. Therefore, you try to see that where you can get the complex cases. So, if you multiply cos with this, you can get imaginary part. If you multiply this with, you get imaginary part. If you multiply this also with imaginary part. So, therefore, that gives you minus 1 by 3 times only imaginary parts, because in the given differential equation this sign corresponds to imaginary part, this is corresponds to imaginary. Therefore, you have to look at the possible outcomes with the imaginary part only. So, this gives you x square minus 26 by 9 into sin 2x, and similarly you have the other case is that 8 by 3x cos 2x, that is your particular integral. With this, we have covered all those possible cases using the operator form. Using operator form, we have covered all possible cases. Okay. So with that, I am closing this session. If you think the content is useful, please like and comment and share the video. Further, in the next video, I'll be covering same non-homogeneous differential equations with constant coefficients using the method of undetermined coefficients. Thank you.